This is a Raspberry Pi running a computer vision model on a neural accelerator, processing about 21 frames per second as it streams video feeds. And whenever it detects a person, it records video and shows detection bounding boxes. You might have seen a few as it happens. I am a very serious consultant, you guys. When I started working as a developer, a web application required a server, and you set it up just so to enable it to do exactly what you wanted. It was Apache, PHP, MySQL, ImageMagick, failed to ban Munin. You'd set up cron jobs for scheduled work, postfix for email delivery. The list just got longer the longer you'd been in the game. And eventually you even realized you had to do SSL, and that was a yearly chore. And you didn't really have anything aside from your own notes to help you reproduce the setup. Maybe you had a list of the tutorials you always went to. Web applications still, to this day, do require a server, in spite of what people tell you. But the role of the server has been boiled down to typically involve very few and very concrete responsibilities. We've run boxes around each service, and we pulled them away from the application server. The database is a separate service. File storage is a separate service. Email is an API provider. And most developers don't operate production systems on the level of the operating system anymore. The things you really need are wrapped up in a container, which you shoot into an orchestrator, and then it runs somewhere over there. Disk is ephemeral. The virtual computer and the container it runs on are both utterly replaceable. It's interesting to me to think that while I was learning about Nginx and whether I should have that instead of Apache and maybe considering Postgres instead of MySQL, the people at Ericsson were running Erlang and mostly handling this stuff from inside of the beam. It was a bare metal world back then, so I'm sure they still had to deal with a lot of OS setup, but I also bet they installed fewer OS packages than I ever did. And overall, I think the cloud approach is fairly sound. Like, you're stripping away complexity from operating the app, and you're optimizing the infrastructure for the common case and for approaches that are known to scale. It makes sense, especially financially. And then we handle the very sensitive and harder to scale database separately, and we deal with the complexities of scaling file delivery separately with like object storage or whatever. But as Elixir devs, we know there are some wins in letting your compute nodes do a little bit more work than typical. We don't always need a separate message queue. We don't always need a go-between to delegate any communication to. The Beam is a very capable runtime, and our libraries and frameworks make use of this. In the end, most cloud systems built in Elixir are structurally very similar to those built in Ruby or in Python, etc. It's N-tier architecture and its horizontal scaling. We use the powers of OTP and Elixir to make all sorts of things better, like database pooling, HTTP serving, metrics, logging, and all that. Open workers are awesome, and we never really need to build a sidecar thing of any kind. And maybe you build some nice special sauce using Erlang distribution or a few gen servers. And some of us do like LiveView a lot. You might have even tried operating an app in a slightly different way. Maybe you put SQLite on that sucker and set up a pet server rather than a cattle farm. It was like, I'm more efficient, I'm on Hetzner. And if you're comfortable with the tools, that is still a perfectly cromulent solution. You can do that. For a Nerves device, you don't really have a choice. You're stuck on a single device, much like a smaller server. And while we usually have a connection to a cloud service or two, the device has a job to do even when the cloud is not there, when it's unreachable. Your thermostat in your home should not stop thermostating just because Wi-Fi died. That's kind of important. So relying too much on the cloud connection is a very straight path to a terrible product. A good Nerves device has to do all the jobs. So if you ever want to really exercise OTP, it's like not all Elixir devs get to do that, but consider dealing with hardware, because then you do. It's OTP all day. So imagine you're building an NVR, a network video recorder, and you have a construction site, a few cameras, and a mission to keep builders safe. You're tracking completion, and you're making cool time lapses at the end. And the device is on redundant power. There's solar, there's batteries. The internet is usually there, but it's 4G, so it's not there. The hardware device is a common single-board computer that you might have heard of. There's a network switch for connecting cameras. There's a 4G modem for connectivity. The cameras are all available via Ethernet. And there's disk storage attached, and there's a fair amount of it. The device does need some UI for configuration and operation. And it needs the on-WIF protocol support for finding cameras on the network. It needs at minimum RTSP protocol support to pull video from the cameras. And to make recordings, the stream needs to be turned into an MP4 file. And you probably want an HLS live stream so you can check on the camera somewhat live. And you have disks to worry about. Whether they're solid state or spinning rust, you have to track how much space you have. You have to deal with retention strategies. And worst case, you have to handle corruption. Construction site power is a very special kind of power. So the worst case situation is always available and ready at any time, because people will just drive over the cable. You will need to update the device remotely without very much disruption. So that has to be in there. And in this age of AI, have you even shipped a product if you don't have edge inference? Absolutely not. So what can we do there? The international symbol for AI, more sparkles. So this device is not a hypothetical. It is an open source project called ExNVR, and it's part of a commercial product, so it's a real thing. The company behind it is Evercam, and it has a lot of stuff going on. I think it's a very good example of an application that does essentially everything it needs within one Elixir app. Note that I don't work for Evercam. They've been very helpful in preparing for this talk, and we've collaborated a bunch in the past. But this talk is not about them or their product, really. Unless you want construction site cameras, in which case, absolutely talk to them. They run Elixir, they're cool, great. But probably a very small group here that needs it. Most of this application was built by Evercam. Recently, I've contributed some parts as I've been doing workshops with this app as an example of a real-world app. So I contributed the trigger system, which we'll talk about, the inference, and a live grid view, which is based on WebRTC work that they already did. The PRs are mostly still in flight, so you can find my fork and go to the good grid branch, because it takes a while to finish up the PRs and get them in without disrupting their business. But the really serious day-to-day working parts were already there when I poked my head in. So they had on-WIF, they had RTSP streaming, they had recording, disk management, HTTP live streaming, a database, a bunch of UI, some API surface area. It was already a complete implementation covering their needs. And it was tested daily by a fleet of hundreds, if not a couple of thousand devices. And they managed these devices on our product, Nerves Cloud, the hosted service that supports the development and maintenance of Nerves Hub, the open source project. So they're a happy customer. I should have forced them to record a very cheesy promotional video, testimonial style, that I could bore you all with, but we'll have to move on because I didn't. What I find good about this, and what I hope you'll enjoy, is that this is a commercial Elixir project that you can download. It's open source. It's completely feasible to use for your own purposes. And if you're learning, you can stand it up with your webcam on your host machine. You don't need hardware, aside from a laptop. And there's plenty of inputs and outputs to play with and explore. Or you can set it up on a Nerves device and use it as an actual NVR, or you can set it up on a PC in a corner, hook it up to a bunch of disks, and use it for real. I did a 5-minute hack where I threw HomeX into it and started throwing JPEGs at Home Assistant from it. Works very well. So it's hackable, it's ready to use. So we're going to go through it a little bit, see what it does. So the database is SQLite, which lets us use Ecto, and everything is fairly familiar if you've done a Phoenix app. The only major difference you might run into compared to your typical Postgres setup is that we run migrations as part of application start rather than before it starts, which is more typical for like a cloud deployment. But on a NERVS device, you don't have a before Elixir starts, really. It's barely there at all. So but in Elixir, it's very easy to control the startup sequence, so it's not really a concern. And we're on a single node, so you don't have this whole pesky contention thing and like, oh, are we doing migrations concurrently? Or none of that. Single node. But it's a vanilla Phoenix app. The database parts are not very large. They're important, but it's nothing you haven't seen before. As the application starts, if there are any camera devices configured that were up and running when it restarted, it will attempt to start them again. If any have been stopped manually, they'll stay down. And setting up a new camera can be done entirely manually by entering a bunch of details, or by on-with network discovery, which will populate the details, assuming you have the credentials for the camera. It's very convenient. So that's my office desk, I suppose. Starting a camera feed is a little bit different depending on the camera. So if you're doing the webcam thing, which is very nice for development, it will start a NIF that captures camera frames and passes them on as H.264 video for the rest of the camera pipeline to use. While the IP cameras, they already offer either H.264 or H.265 over RTSP, so you mostly decode that and use that. And then there's a debug feature where you can actually just shove a video file straight into it and use it as a camera for testing. But in the end, you get either H.264 or H.265 video streams, so that's what the pipeline supports. And once you have a stream of H.265 something coming in, we're in the beginning of the membrane pipeline. The pipeline is called main, which feels like a C program, but it is the central piece, so I suppose it makes sense. How many here know what membrane is? How many have used membrane? Oh, yeah. It went from half the room to 5%, maybe. Fair enough. Most jobs don't require a media framework. But in brief, Membrane is a very cool media streaming framework built in Elixir. It deals with all the pains of audio and video so that you can build interesting applications with it. The real setup for this pipeline happens in this handle child notification function, which kind of seems weird, but it's because the pipeline is only constructed once the actual video stream is available and we know that we have tracks. And it's a slightly different thing if it's a substream or a mainstream, and this is a distinction common for IP cameras. The substream is a lower quality, less demanding stream. The mainstream is usually, for the cameras I've been using, full 4K and stuff, so it's annoying to deal with. The pipeline immediately specifies a T-junction for splitting off data, and the element can split off data to any number of receiving elements, and we can see that the main feed includes an HLS sync for HTTP live streaming, storage for recording video segments, a snap shooter element that's used for some UI preview stuff, a video stream stat reporter, a WebRTC output, and optionally, if configured, you also get a ring buffer for event recording and an inference pipeline. And the subfeed is essentially identical, but it does one thing the main doesn't, which is thumbnail extractions, or for some reason called BIFs. I don't remember what that is. I think it came from some other video device, the terminology. But there are two variations of streaming video available here. So WebRTC is the more experimental one, while HLS is very tried and true. To my knowledge, Evercam mostly uses HLS, but I could be wrong. But HTTP live streaming is an older definition of live. So if you've ever dealt with this, it is a very scalable approach. It allows clients to buffer the stream, and essentially you produce a playlist of available video chunks, and you keep updating that playlist as you stream, but you provide the chunks as separate files. So whenever a chunk is ready, that's when you add it to the playlist, and that's when people can fetch it. This means the chunks can go on object storage or a CDN, and be distributed worldwide. Like that's what an Apple announcement video is. That is what a YouTube stream is usually. But this is not the use case here. But when you're dealing with LTE or 4G, it's actually very nice to be able to buffer the video, like, okay, let it catch up a little bit. A drawback is that you'll have many seconds of latency. It can be quite a few, depends a lot on the processing pipeline and sort of how resilient you want it. But HLS is really useful, but it depends on your use case. WebRTC, on the other hand, is very low latency. It's live and it's lively, and it is what we use for conference calls in regular society all the time. It uses UDP instead of TCP, which is awesome for maintaining that low latency. And when it works, it's lovely. As you might know from having used video conferencing tools, there are way more things that can and will go wrong with WebRTC. So, trade-offs. I added the grid view as a live feed since I wanted to show immediate things. But you only get the frames you get, and you can't jump back in time. You can't buffer to get smooth future play, so it's trade-offs all the way down, but that was built on top of the WebRTC. Now, gloriously enough, you can get both out of Membrane from the same stream of frames. So there are sharp edges in all this stuff, but Membrane really does a great job of providing you a lot of capability. What was particularly compelling about the Membrane pipeline structure is that when I wanted to prototype the inference feature, I just grabbed the thumbnailer element from the BIF and just told it to send off those images to a gen server on the side, and my gen server ran the Elixir YOLO library on it, and that totally worked. I got the images, I got the data, but it was a hack. But it was a quick hack, so I got started quickly. As I wanted to actually show this as a proper thing, I wanted a live camera view, and that's where WebRTC comes in. So I wanted to draw fancy bounding boxes with LiveView on the WebRTC view. So I shoved the WebRTC view into the LiveView, and then I started throwing the detection information out over Phoenix PubSub as broadcasts that the LiveView could then render. It worked, but detection was slow, and the results were kind of iffy. If you can't read the label, it says horse. It's 79% sure. For minutes on end. Straight front facial shot, horse, thanks. What made detection slow was a whole slew of things I was doing wrong, so it took like a second and a half or something. I was running it on CPU, which worked kind of okay on my beefy Linux machine back home, but when I configured it to instead use the NVIDIA GPU via XLA, it was definitely faster. Amusingly, it's faster on this M2 MacBook Air than it is on my NVIDIA 3090, which I think is mostly the whole shared memory and overhead thing. We'll also return to the Raspberry Pi on that note later. But there were some pre-processing stages I could also trim out. So instead of shipping JPEGs, I could use tools that exist in ExNVR to request the correct pixel format, dimensions, and padding that the YOLO model wants. Lots of thanks to Alvise. Are you here? No, he's sleeping. But the man behind the YOLO library in Elixir helped me out a bunch. And with this, I could cut out heavy dependencies like eVision or image for processing, and the horse detection issue went away, because when I wasn't doing padding, essentially the model ran on a distorted image. So all this main I have, and then you extend me. Yeah, I suppose that's what happened. That's the theory anyway. So once I could see that that inference itself was fast in terms of time spent, and it generally identified me as a human, I started to see that the detections were still not current. They lagged behind quite a bit. So I threw out my hacked up thumbnailer and implemented a new membrane filter called the frame picker, and a membrane thing called the object detector. So at this point, I'm making a proper membrane pipeline. We're upstanding citizens now. The object detector only demands a single frame at a time. This is not typical for membrane elements. They usually ask for like 100 just to get things rolling. But this just wants one frame. Again, we want things current and low latency. So the frame picker will hold on to the latest frame it receives, throwing away the previous one continuously. So when the object detector finally completes its work, a bunch of frames will have passed by. But the frame currently in the picker is fresh, it's recent, and it will be passed in for object detection. So this is load shedding, classic technique for maintaining performance under load, but in this case it's not a failure mode, it's quality of service. This is how we maintain low latency. This trade-off is that we don't analyze all the frames. We could do that later if we wanted to, if we ever have idle time. And the latency from frame at camera to detection B-box showing on the LiveView is essentially pipeline time plus inference time plus notification time plus some fraction of the time between the camera frames. And thanks to the beam, all of these are quite low and quite consistent. So there's actual minimal waiting. It's quite snappy. And importantly, the inference pipeline is not synced or tracked with the WebRTC pipeline. They are both going full tilt, working as fast as they can to give you the most current results. And then we just overlay them on top of each other. So the inference speed doesn't block the video, and the video does not block inference. We fork the directed graph kind of early on and do separate processing. So the WebRTC feed can run at whatever frame rate is appropriate for it, and the inference will do the same at whatever frame rate it can achieve, is usually the case. So the end result is very reasonable for the human watching it, even if it's kind of weird under the hood. There is a massive efficiency elephant in the room here, especially if you know media streaming and you know some of stuff about the beam but not know it that well. What you might have heard is that we do immutability. There's no shared state. There's message passing, which means everything is copied around, right? A camera stream of 30 frames per second would mean 30 large binaries per second copied every time across a process boundary, which is on every step of the membrane pipeline, for every pipeline in the T. Memory usage would blow up, the GC would work itself to death, and life would suck. That's where we would be, except there's one little optimization. Anyone here know what that is? Yeah, ref-counted, or also known as big binaries, an optimization that defines a binary as big if it's larger than 64 bytes, which I wonder when that happened. But these are not copied around in the beam. They're reference counted and stored outside of local process heaps, and all we're passing around through these pipelines are references. It's glorious and entirely transparent. We don't even know it's happening unless we look under the hood. And this is how you would essentially implement the same thing in C. It is almost like we're using a high-level C framework. I like to call that framework Erlang. If you know any C, actually look at ErlNIF. It's a fantastic framework for building C applications. It seems like, from my perspective. I'm not a C developer, really. I just pretend a lot. But it also goes deeper than you might expect. So you can't feasibly do all this media processing in Elixir, and these codecs are like the darkest of arts. So Membrane and ExNVR delegate to FFmpeg and the related libraries for some of this, much of this. And this requires NIFs. Looking into ExNVR's included video processor library, if you follow the NIF, you'll see that it passes the reference data through to FFmpeg C APIs. And FFmpeg reads that data to produce a processed frame. So it's zero copy through the entire pipeline and straight down into the bindings. Very nice. So only new binaries actually have a cost. And this is similar to what Paulo Valente and the gang are doing with NX tensors and transferring them into Python X and all this type of stuff. And this optimization is critical for the design of Membrane to work well. Anyway, we're now doing inference, but we're not doing edge inference if we aren't doing it on a Raspberry Pi, because that's the only embedded device people know about, right? So what does that take? Well, on the first iteration, I just moved it onto the Raspberry Pi and ran it on the CPU, and it did about half a frame per second. Who here has heard about the Raspberry Pi AI Kit? Or the AI Kit Plus? Or the AI Kit Plus 2. Don't buy the AI Kit Plus 2. We don't have support for that yet. They broke compatibility. Anyway, I need to buy one, I suppose, but they're expensive, and I don't want to. Anyway, the solution is always to plop an AI accelerator down on the thing. And so I forked Paulo and Vittoria's work on NX Halo. We'll unfork it. It's in progress. It's a whole thing. But after a bunch of nonsense to get the Halo tools lined up, so this is the actual accelerator, it essentially just worked. I had the same pipeline structure, but I made a separate detector module that called the hardware libraries instead. And last I measured, it was about 22 FPS, or 11 FPS each with 2 cameras. And this is doing batches of a single frame. It would be way faster if I sent it multiple frames at a time. But you'd lose latency. And there might be more we can squeeze out as well. But we have it. We have edge inference. We have successfully disrupted the edge. With that important job done, we can explore a few other things. So the trigger system. A trigger in this system that I brained up is a combination of any number of sources and any number of targets. It is very often just one source, one target, but supporting multiple kind of makes sense. So an upcoming feature that is a good example of a trigger source would be on-whiff events. So if your camera has support for like on-camera detection or maybe a tamper sensor, so that if people mess with your camera, you get told about it. Then the NVR could react to those events. And you could hook them up to whatever behavior you wanted, essentially. And something we have already is just straight-up API calls. They're called events, which is very generic and vague. But you can expose a trigger for starting recording, another for stopping recording, and you can make the device log the event to the device logs. Like, we have some basic sources and triggers. Or a source can be inference detection, where you set a threshold for the detections or set what classes you care about, and then you set up that as a source. And maybe you trigger a recording for a camera that is not constantly recording, because that takes a lot of disk space. And usually nothing is happening, at least where I live. And it starts recording. So you set up the trigger to record, and it would start recording when it has seen the source trigger fire. And then after, say, 30 seconds without a trigger, it would stop recording again. And here we also can see, if the video is grokkable, you can see that you get to set a buffer of how many seconds to keep. And that's the number of seconds ahead, before the event that you get. And we'll get back to that. Probably my favorite feature, actually. So the ways that trigger sources fire is fairly varied. So there are hooks like in the API calls, or there's some inference or whatever, but they all just broadcast an appropriately scoped Phoenix PubSub message. And we have a listener gen server that just grabs those triggers, runs the intended targets. It's all pulled from the database. There's nothing fancy going on because it doesn't have to be. That part is very straightforward. Like, the plumbing is uninteresting fundamentally. But the way you do good on-event recording is fun. So I learned this video buffering trick from the ancient Python libraries for the Raspberry Pi original camera. So they had a cool ring buffer-based recording, which would mean you would ask the device to record a clip, and it would get you some amount of seconds before the clip. And if you tune this wrong, your Raspberry Pi would absolutely crash, because that sucker had no memory. But by using a circular data structure like this, you can ensure that you don't use too much memory, and you can provide some video from before the event happened. You just keep writing it to memory and keeping it in memory. The default nerves logger, ring logger, works very similar to this as well. So ours is a bit more complex than log messages, so I ended up needing to use the Erlang Q module to implement this in some reasonable fashion, because not all frames are equal. Some of them are key. They're called keyframes. And the other ones are called p-frames or interframes. And this is why media is so fun. And If you've ever seen that you can't seek to the exact frame you want in a video, then the video player only cares about keyframes and ignores the in-between ones. Because having a p-frame without a keyframe is like having a diff without having the original file. You can't really make any good use of it. So our buffer needs to be keyframe aware. It needs to drop a keyframe. If it needs to drop a keyframe, it should also drop all the p-frames that depend on it, because they're useless now. So it needs to be a little bit smarter than just giving you random p-frames in the middle of nowhere. What is really nice is that this is very smooth to implement in Membrane. So we have this circular buffer that doesn't pass on any frames. But the moment we want to record to disk, we already have a recording element ready and set up. It's starving. It's just waiting to get to write something to disk. And the moment we get the pub/sub notification that, oh, time to record, we just flush all of those to the recording element, everything we're holding. That gets recorded, and then we open the gate and just start passing the frames through as they come in. And when a timer times out, we close the gate again. If another trigger event comes in, we reset the timer. It's very basic, which makes it easy to reason about. And once it's up and running, it's quite nice to work with. So for example, as long as a person is visible, it will keep recording. When a person hasn't been visible for, say, 30 seconds, it will stop. That's essentially the feature. And it works surprisingly well for surprisingly little code. Of course, you could hook up a different source, like a presence sensor or a door switch or something, and trigger the recording off of that, and the same behavior. Now, the parts I built for this were initially for my own purposes, but since I wanted them to fit well into the commercial product that they're actually using this for, I removed the whole cyberpunk bounding box that was hard to read and kind of edgy, and tried to add something a little bit more potentially professional. So I added configurable styles. This is a very silly feature, but it's fun. And the last one uses like the CSS frosted glass filter type thing, so it's ridiculous. But this is what LLMs are actually for, generating bounding box graphics, because they seem highly tuned for that. You should definitely try it. It's almost like they're prepared for dystopia somehow. The trigger system is not a massive workflow type thing with multiple stages, but it is sufficiently flexible. It's easy to add new configurable sources and targets. I might want to make a plugin system at some point, but it's overkill for now. And if Evercam adds on-with events, they'll easily be able to hook this up. And you just implement a behavior, you add a module to a list, and ta-da, new trigger source or trigger target. It's very straightforward. And the various kinds of inference are implemented very similarly. So one thing I found interesting about this crude polymorphic type of setup is that we have functions for exposing configuration values, and we generate the forms based off of those. And even supporting custom widgets like the bounding box selector is quite straightforward. And then it all goes into a map field. Like there's nothing unexpected or special going on here. And it comes with the usual trade-offs about using a map field. That you might be familiar with. Now, particularly for the inference, there's one callback that is slightly more interesting. It's called build spec. It will, when you're building your pipeline, if this inference is part of your pipeline, it will add in those, the inference pipeline. So your pipeline is modular at runtime. And this was very straightforward because Membrane is intended to do this. Now, we do it the simple way, where we build the whole pipeline every time we restart the device. But you can add and remove Membrane pipelines dynamically, so we should probably just do that, but not yet. The models we've used are just off-the-shelf YOLO models. There's nothing particularly novel or fascinating there, though you could bring your own. Like YOLO is a very generic thing. You could do many things with it, detect car plates or whatever. And fundamentally, there's nothing novel here. It's kind of the trick of this whole thing. Because if you know about frameworks and tools already, you already know that Elixir can and will do all this. And the people who work on ExNVR have put a lot of elbow grease and effort in to make this a good thing for them to work on. They made it smart. They adapted it to their use case. But fundamentally, we know that Elixir can do media. We know that it can do the NX stuff. What might not be obvious is that it can do all of them at the same time on the same computer. So you can actually just build your whole application in a single node. And this has not been boiled down to the bare essentials, the way cloud deployments has. And in some cases, it makes sense to build Elixir applications this way. Some people will look at it and say, oh, that's a ball of mud. The truth is, any application you did not build is initially always a ball of mud when you approach it. But the physicality of an embedded device forces a lot more code to be local. So this would not be an NVR if it just best effort streamed to the cloud continuously. It has a job to do, and it should do it as well as possible in the face of failures. Hard realities like power interruptions, full disk, missing internet access. The cloud is important for a lot of the good features of like the Evercam product, but you don't want it to be a requirement for it to keep recording. I used to do Python, and it's a relatively popular embedded tool due to the Raspberry Pi, where all the libraries are Python libraries. And because learning and education does Python, a lot of people pick it up, and the Raspberry Pi was originally about learning and DIY. Now, Python has web frameworks. It has Django, Flask, Datastar, and a couple of hundred others. And they all do stuff to try and get concurrency on par with Node.js. Because apparently that's the bar for some reason. They're slower, but just like Node, they're doing cooperative multitasking, the lesser kind of multitasking. And this means the slow pieces of work block most other pieces of work. And this shapes your entire architecture, because only I/O and special blessed paths get to happen in parallel. So performance is immediately challenging for a system like this. There are variants of LiveView, of course. Let's leave it at that. I'm not convinced by any of them. But then there's WebRTC tools. You can absolutely bring in some tool from the ecosystem, some new library or framework to do WebRTC. And because of the size of the ecosystem, you even get a bunch of options. Of course, none of them are general dynamic media frameworks like Membrane, because doing so would be incredibly painful. Or if they are, be very mindful about the performance considerations. You can bring in GStreamer, you can bring in FFmpeg and friends, but it is always painful to string those together, and it's complex. And the separate tool means a separate event loop to marry to Django, which would cause too much trouble and wouldn't be parallel. So instead, you start an entirely new OS process, and now you need a way to communicate between them. So now gRPC or HTTP or CRMQ or a message bus and many other options are suddenly on the table, and you have decisions to make. Doing background work, you can do cron and stuff, and this is more important because you can't just kick off a task within your Elixir app because you're in Python. So you might grab Celery, or you can actually get Oben now, but I think you need Postgres for that one. They're talking about that in another room right now. Storage monitoring would be another cron job or another worker process. And inference, well, you need to protect the singular resource, the accelerator, so probably a queue via some broker and a worker process performing that inference. And what we use a gen server, a membrane element for, requires infrastructure. In our case, the runtime is infrastructure. The nuanced stuff, like dynamically starting bits of the pipeline only when inference is actually set up, you'd skip that. You'd go for something way simpler because it's painful to set up, and it builds out your whole architecture. And this ends up being the architecture of a lot of embedded Linux devices, some RPCs, APIs, some queues, some brokers, a whole pile of worker processes. I've seen a few of these with clients. And Robert Verding's first rule of programming strikes again. Any sufficiently complicated concurrent program in another language contains an ad hoc, informally specified, bug-ridden, and slow implementation of half of Erlang. You've just built half of Erlang locally on a single machine. So all this stuff for a single machine, and you don't get me wrong, half of Erlang is still cool and useful, because it is. But it is not cooler or more useful than all of Erlang. Thank you for listening.